There is a moment, right before your thumb and finger close around a tick crawling on your skin, when you feel a small surge of satisfaction. You caught it before it bit. You are about to end its life and move on with your day. But that single squeeze, that tiny crunch between two fingertips, might be doing something far more dangerous than the bite you were trying to avoid. Because the tick you just crushed was not the threat. The tick was the messenger, and what it was carrying, and what allowed it to be there in the first place, points to a much larger and far more unsettling problem unfolding in the woods, fields, and backyards around you. Ticks are not insects, even though most people lump them in with mosquitoes and fleas. They belong to the arachnid family, the same broad group as spiders and scorpions, which means they have 8 legs as adults, and no wings, no jumping ability, no real means of chasing anything down. A tick cannot fly toward you. It cannot leap from the grass like a flea. Instead, it performs something scientists call questing, where it climbs to the tip of a blade of grass or the edge of a leaf, extends its front legs, and simply waits, sometimes for weeks, for a passing body of warmth and carbon dioxide to brush past close enough to grab onto. It is patience taken to an extreme that few other creatures on Earth can match, and that patience is part of what makes it such an effective biological courier. A single tick can carry more than one pathogen at a time, a phenomenon researchers call coinfection, where the same bite can transmit Lyme disease alongside anaplasmosis or babesiosis in a single puncture. But here is the detail almost nobody talks about when they panic and crush the tick on their arm. The tick itself did not invent these diseases. It picked them up from somewhere. Ticks are not born infected. A tick hatching from an egg is, in the vast majority of cases, completely clean, carrying nothing harmful at all. It becomes a carrier only after it feeds on an infected host during an earlier stage of its life, usually as a larva or nymph, often biting a small mammal long before it ever reaches a human. Which means every infected tick is really just evidence. Evidence that somewhere nearby, an animal reservoir of disease is thriving. That reservoir, in most temperate parts of North America and Europe, is overwhelmingly made up of small rodents. White-footed mice, in particular, have become the subject of intense scientific scrutiny because they are remarkably good at carrying Borrelia burgdorferi, the bacterium responsible for Lyme disease, without getting sick themselves. Their immune systems tolerate the bacteria in a way that larger mammals do not, allowing them to function as walking incubators. A young tick larva feeds on an infected mouse, picks up the bacteria, molts into a nymph, and then seeks its next blood meal, which is frequently a human being working in the garden or a dog returning from a walk in the woods. Researchers studying these transmission chains in Connecticut and New York found that rodent population booms in 1 year reliably predicted spikes in infected nymph density the following year, creating a forecasting tool that lets scientists essentially predict bad tick seasons based on how many acorns fell 2 autumns earlier, since acorn abundance drives rodent population growth, which in turn drives the number of ticks carrying disease. This is the bigger problem hiding behind the tick on your arm. It is not really about the tick at all. It is about an ecosystem that has lost some of its natural checks on rodent populations. Foxes, hawks, owls, weasels, and snakes used to keep mouse and vole numbers in balance across much of the temperate world. As forests have been fragmented into smaller patches by roads, subdivisions, and agriculture, many of these predators have either disappeared from those fragments entirely or become far less effective at controlling rodent numbers within them. Small forest patches surrounded by human development tend to lose their top predators first, while small rodents, which can survive on the edges of yards and gardens, often thrive in those same conditions. The result is what ecologists sometimes refer to as the dilution effect working in reverse. In a healthy, biodiverse forest, ticks have many possible hosts to feed on, including some species, like certain birds and larger mammals, that are poor reservoirs for disease and essentially clean the pathogen out of the tick population by diluting the proportion of ticks that pick up an infection. But in a degraded or fragmented habitat dominated by white-footed mice, that dilution disappears, and the percentage of ticks carrying disease climbs sharply. There is a particularly striking piece of research connecting this directly to deer populations as well, although the role of deer is often misunderstood. Adult ticks need a large mammal for their final blood meal before laying eggs, and white-tailed deer are the preferred host for adult Ixodes ticks across much of the eastern half of North America. Deer themselves are poor reservoirs for Lyme disease, meaning they do not typically pass the bacteria back into ticks that feed on them, but they are essential for tick reproduction, since a single female adult tick can lay several thousand eggs after a successful blood meal. As deer populations have exploded in suburban areas over the past several decades, partly due to the loss of large predators like wolves and partly due to hunting restrictions near residential zones, the number of adult female ticks able to complete their life cycle and reproduce has climbed right alongside them. So when a homeowner finds ticks crawling across their porch, they are often looking at the downstream consequence of 2 overlapping population surges, rodents providing the infection and deer providing the reproductive fuel, both made possible by the absence of the predators that once kept each of them in check. Killing the individual tick on your skin does nothing to interrupt this chain. It removes one data point from an enormous and self-sustaining cycle that will continue regardless of what happens to that single arachnid. In fact, some researchers studying citizen tick submissions have used squashed and intact ticks alike to map disease prevalence across regions, since the genetic material of the pathogens often survives even after the tick itself has been crushed, which means the information embedded in that tick can actually be more useful to public health tracking than the act of killing it ever was for personal safety. Several university extension programs and state health departments now actively encourage people to submit ticks they find on themselves or their pets for testing rather than simply destroying them, because each submitted tick adds another point of data to maps that track where infection rates are rising, which in turn helps researchers identify the rodent and deer population hotspots driving the problem in the first place. None of this is an argument for romanticizing the tick itself, or for letting one continue feeding once it has been found attached to skin. Removing an attached tick promptly, using fine-tipped tweezers to grasp it as close to the skin as possible, and pulling straight up with steady pressure remains the correct and medically recommended response, since the risk of pathogen transmission generally increases the longer a tick remains attached, with many infections becoming significantly more likely after roughly 36 to 48 hours of feeding. The point is not that ticks are harmless, or that they deserve protection in the same way an apex predator or a pollinator might. The point is that public fear and frustration tend to focus entirely on the visible, crawling nuisance, while the structural cause sits quietly out of sight, scurrying through leaf litter and underbrush, mostly unnoticed and almost never blamed. Consider what this means at a landscape level. Areas with intact predator populations, healthy forest interiors rather than fragmented edges, and diverse mammal communities tend to show measurably lower rates of tick-borne infection, even when the raw number of ticks present is similar to more degraded areas nearby. This has led some conservation biologists to argue that restoring predator populations, protecting larger unbroken tracts of forest, and managing deer densities more aggressively in suburban zones could do more to reduce human Lyme disease risk over the long term than any amount of personal tick removal or pesticide spraying ever could. It is a strange and almost counterintuitive idea that bringing back the very predators many people are instinctively uneasy about, foxes prowling through a subdivision, hawks nesting near a cul-de-sac, could end up making the neighborhood measurably safer from a disease most people associate with hiking trails rather than backyard ecology. The tick, in this light, becomes something closer to a warning light on a dashboard than a villain in its own story. Its presence, and especially the rate at which the ticks in a given area test positive for disease, reflects choices made decades ago about land development, predator control, and forest fragmentation, choices most homeowners never had any direct hand in, but now live with, every time they walk through tall grass. Squeezing the life out of one tick on a forearm provides a brief sense of control over a problem that is, in truth, ecological rather than individual, rooted in population dynamics playing out across entire counties rather than on a single patch of skin. The next time you find one crawling toward an open collar or tucked behind a knee, it might be worth remembering that the real story is not the eight-legged hitchhiker itself, but the much larger and much quieter imbalance in the woods nearby that put it there in the first place. If creatures like this fascinate you as much as they fascinate us, make sure you are subscribed, because there is always something stranger and more interesting waiting just beneath the surface of the natural world.